Meteor is an active radar-guided beyond visual range air-to-air missile, VRAM, being developed by MBDA. Meteor will offer a multi-shot capability against long-range maneuvering targets in a heavy electronic countermeasures (ECM) environment with range in excess of 100 km, 62 miles. It is intended to equip the Eurofighter Typhoons of the United Kingdom Royal Air Force, RAF, and the Royal Saudi Air Force, German Air Force, Spain's Ejercito del Aire, Italian Air Force, British and Italian F-35s, Dassault Rafale of the French Air Force, Saab JAS-39 Gripen of the Swedish Air Force, Czech Air Force, Dassault Rafale of the Indian Air Force, Egyptian Air Force and Qatar Air Force. It entered service in the Swedish Air Force in April 2016, with the SWAF as the first operator of the missile due to most testing having been done on the JAS-39. It officially achieved initial operating capability, IOC, with Swedish Air Force Gripens in July 2016, and it was announced at the Farnborough Air Show that the Czech Air Force would soon reach IOC as well. According to MBDA, Meteor has 3 to 6 times the kinematic performance of current air-air missiles of its type. The key to Meteor's performance is a throttleable ducted rocket, ramjet, manufactured by Bayern Chemie of Germany. History. From the outset, the Meteor program has been the main catalyst for the consolidation of the European complex weapons industry. Of the 7 European companies who responded to the initial request for information, RFI, from the UK Ministry of Defence, MOD, either individually or as part of a team, 5 are now part of MBDA and the other 2 are major risk-sharing partners on the program. The selection of Meteor ended a long-running and hard-fought competition between Europe and the United States, US, and gained Europe a significant foothold in a market sector hitherto dominated by the US. The first fighter airplane to equip this new missile system was the Gripen fighter aircraft in 2016. Requirement. Meteor was selected in competition to meet the UK's staff requirement, Air 1239, SR, A 1239, for a future medium-range air-to-air missile, FRAM or FRAM, to replace the RAF's B-Dynamics Skyflash semi-active radar-guided missiles. As the primary air-to-air armament of Eurofighter, the missile would be used against a range of fixed and rotary wing targets including unmanned aerial vehicles and cruise missiles. Although no detailed performance requirements have been publicly released, they were understood to demand launch success and no escape zones 3 times greater than those of the then state-of-the-art medium-range missile, AMRAAM. The missile external geometry would be constrained by the need for compatibility with Eurofighter's semi-recessed under-fuselage launchers which had been designed for AMRAAM. Key features of the requirement included stealthy launch, enhanced kinematics, which will provide the missile with sufficient energy to chase and destroy a highly agile maneuvering target, robust performance in countermeasures and the ability for the launch aircraft to fire and disengage at the earliest opportunity, thus enhancing aircraft survivability. These requirements were largely shaped by the perceived threat posed by advanced versions of the Russian Sukhoi Su-27 flanker armed with extended-range ramjet-powered versions of the R-77 missile. In February 1994 the UK MOD issued an RFI on the possibility of the development of an advanced medium-range air-to-air missile. 4 concepts were produced in response, all using integrated rocket/ramjet propulsion. A group led by B, comprising Alenia Difsa, GEC Marconi, and Saab Dynamics, proposed the S225XR, Matra proposed a derivative of Mica. Although the long-planned merger of B Dynamics and Matra's missile division was expected to lead to the removal of this proposal, Daimler-Benz Aerospace and Bayern Chemie proposed the Advanced Air-to-Air Missile, A3M, and Hughes, supported by the U.S. government, proposed an AMRAAM derivative based on upgrade work being carried out. The competition commenced in June 1995 with the endorsement of SR, A, 1239 by the Equipment Approvals Committee, EAC. This took place against a backdrop of government and industrial contacts between the UK, France, and Germany aimed at establishing a common requirement and an industrial consortium. Even at this early stage the competition was developing into a straight fight between a European and a US solution. The US government agreed to transfer development of the advanced propulsion system to the UK in support of the Hughes bid, although it was not clear how much of the actual work would be allowed across the Atlantic. Hughes' initial offering for SR.A. 1239 was powered by a variable flow duct rocket, VFDR. This had been under development by an Atlantic Research/Alliant Tech Systems team for 10 years, but the US Air Force had no plans at that time to develop an extended-range AMRAAM, since this could endanger support for the stealthy F-22 Raptor. The team had also provided information to B, who were considering the VFDR as a power plant for the S-225XR, along with systems from Bayern Chemie and Volvo. Atlantic Research had discussions with Royal Ordnance, the only UK company with the necessary capability following Rolls-Royce's decision to stop work on ramjets. On October 2, 1995, the Minister for Defence Procurement gave approval for an invitation to tender, ITT, which was issued by the MOD in December. Responses were due in June 1996 for a UK contract valued at £800 million. By February 1996 the US team was in place, whereas the European effort remained fragmented. Matra and DASA's missile division, LFK, were on the brink of a joint bid, which B and Alenia were also considering. The Matra/LFK proposal was based on Matra's Microstique project using a Matra/Onera designed self-regulating solid fuel ramjet. The merger between B and Matra's missile businesses had stalled due to the French government's reluctance to approve the deal without UK assurances that it would adopt a more European approach to procurement. A joint winning bid for SR.A. 1239 was expected to provide renewed impetus to the merger, both companies having had to restart the valuation process due to changing fortunes since the deal was first agreed, over 2 years previously. This was not the only merger in prospect, as DASA and Aerospatiale were conducting due diligence, although Matra had also expressed an interest in Aerospatiale's missile operations. The German government was trying to use the UK and German requirements to forge the consolidation of the European industry into a critical mass capable of engaging the US on more equal terms. Hughes had assembled a team including Aerospatiale, Propulsion, Shorts, Integration and Final Assembly, Thomson Thorn Missile Electronics, TTME, Fokker Special Projects, Fin Actuation, and DLBGT Defense, Warhead. Incidentally, the adoption of FMRAAM as the name of Hughes' proposal forced the UK MOD to change the title of SR.A. 1239 to VRAM. Hughes would provide the seeker, with electronics from its Scottish subsidiary, based in Glenrothes. The upgraded guidance electronics would be compressed compared to the existing AMRAAM. Other changes included a new electronic, as opposed to the usual mechanical, safe and arm device, based on DLBGT Defense's IRIST system, a TTME digital target detection device, a two-way conformal microwave proximity fuse unit, and a shortened control and actuation system. The seeker and warhead were basically unchanged from AMRAAM's. The European content of Hughes' bid had been bolstered by the replacement of the ARC/ATK VFDR by an Aerospatiale Celerg liquid fuel ramjet with an ARC-integrated nozzle-less booster. This was based on studies conducted during the Simple Regulation Ramjet program, which began in 1994. The direct injection design used an inflatable elastomer bladder within the fuel tank to control the fuel flow and was believed to offer a lower cost approach compared to a regulated liquid ramjet requiring a turbopump and associated fuel supply hardware. 80% of FMRAAM production and development would be carried out in Europe, 72% in the UK. The European team, consisting of B Dynamics, Matra Defence, Alenia DIFSA, GEC Marconi, Saab Dynamics, LFK, and BC was finally assembled just 6 weeks ahead of June 11, 1996 deadline for bids. B brokered an agreement whereby it would lead the team. This tie-up avoided a dangerous division in the European attempts to provide a credible alternative to the US bid. Matra and LFK had already teamed and would have bid independently, had Bay's shuttle diplomacy failed, seriously denting European credibility and giving Hughes the advantage. B Dynamics' original S225XR proposal was a wingless design. However, during the international discussions the evolving UK and German proposals were found to be near identical in concept apart from the latter's wings. The trade-off between winged and wingless configurations was very closely balanced, but the wings offered increased roll damping, which was believed to be useful given the asymmetric intake configurations, so the German A3M configuration was adopted for the European proposal, called Meteor. When the bids went in, it was anticipated that a contract would be awarded at the end of 1997 with first deliveries by 2005. Risk reduction. Following several rounds of bid clarification, it was concluded in early 1997 that the risks were too high to proceed directly to development. The UK's Defence Procurement Agency, DPA, and Sweden's Defence Materiel Administration, FMV, therefore launched a Project Definition and Risk Reduction, PDRR, program. This gave the two teams 12 months in which to refine their designs, and identify and understand the risks and how they would be mitigated. PDRR contracts were placed in August 1997 with a second ITT following in October. The results of the PDRR program were expected in March 1998, but the procurement became ensnared in the run-up to and aftermath of the UK general election in May 1997, as the new Labour government conducted its Strategic Defence Review. By 1998 the in-service date, ISD, defined as the first unit equipped with 72 missiles, had slipped to 2007. The UK MOD hosted a government-to-government level briefing on 14–15 July 1997 with Italy, Germany, and Sweden to discuss the VRAM program and how it might meet their requirements, with the aim of pursuing a collaborative procurement. There were issues at this time over the funding of the risk reduction contracts, and some nations were discussing possible financial contributions to the studies in return for access to the data. The European team hoped that, if chosen by the UK, Meteor would also be adopted by Germany, Italy, Sweden, and France. However, Germany had now formulated an even more demanding requirement. In response, DASA/LFK proposed a modified A3M, called URAM, using a DASA-ULM K-band active seeker, with a passive receiver for stealthy engagements, and a redesigned Bayern-Chemie propulsion system. The high energy of the high-frequency radar, compared to the I-band used on AMRAAM, was claimed to provide an ability to burn through most ECM, and the shorter wavelength would allow the target's position to be determined more precisely, allowing the use of directional warheads. At one stage DASA was pushing their government for a 2-year demonstration program which would culminate in 4 unguided flight tests. This was presented as a fallback position in case the UK chose Raytheon's proposal. More cynical observers regarded this as a tactic to push the UK towards Meteor. Revised VRAM bids were submitted on May 28, 1998, with final reports in August. The US Secretary of Defense, William Cohen, wrote to his UK counterpart, George Robertson, with assurances that procurement of the Raytheon missile would not leave the UK vulnerable to US export restrictions, which could potentially handicap Eurofighter exports, a major concern highlighted by Meteor supporters. The letter assured open and complete technology transfer, adding that VRAM would be cleared for countries already cleared for MRAM and that a joint commission could be set up to consider release to other sensitive countries. In July 1998 a formal statement of intent was signed between the governments of the UK, Germany, Italy, Sweden, and Spain which, subject to the UK's selection of Meteor, agreed to work towards joint procurement of the same missile. In September 1998, Raytheon supplied the UK with estimated costs for AIM-120B AMRAAMs to be fielded on Tornado and as an interim weapon on Eurofighter on initial entry into service while VRAM was still in development. The US declined to sell the improved AIM-120C version. This was the first stage in Raytheon's incremental approach to fielding the full capability VRAM. The MOD had offered both teams the opportunity to propose alternative acquisition strategies which would have involved reaching the full capability on an incremental basis by initially providing an interim capability which could later be upgraded. Raytheon's staged approach to meeting the full SR.A. 1239 requirement offered an interim weapon with a capability between the AIM-120B AMRAAM and the FMRAAM. The Extended Range Air-to-Air Missile, ERAM, had the FMRAAM seeker and guidance section mated to a dual-pulse solid propellant rocket motor. Raytheon estimated that IRAM could be ready by the then Eurofighter ISD of 2004 and provided 80% of the FROM capability but at only half the price. This approach played to perceived mod budget limitations and a realization that the main threat on which the SR.A. 1239 requirement had been predicated, the advanced R77 derivatives, did not look like entering development anytime soon. An incremental approach would allow any technological advances to be incorporated into future upgrades. These could have included multi-pulse rocket motors, thrust vectoring, hybrid rockets, gel propellants, and ductless external combustion ramjets. The Meteor team had considered an interim design, also powered by a dual-pulse solid rocket motor, but decided to offer a fully compliant solution, believing that the staged approach was not cost-effective due to concerns that upgrading from one version to the next would be more complicated than Raytheon claimed. In February 1999, Raytheon added another interim level to their staged approach. The AIM-120B and would feature the IRAM/FROM seeker and guidance section but attached to the AIM-120B solid rocket motor. This would be ready for Eurofighters 2004 ISD and could be updated to the IRAM or FROM configurations in 2005 and 2007 by swapping the propulsion system and updating the software. At the 1999 Paris Air Show, the French defense minister expressed his country's interest in joining the Meteor project, putting further pressure on the UK to use VRAM as a focus for the consolidation of the European guided weapons industry. The French offered to fund up to 20% of the development if Meteor won the UK contest. Intergovernmental letters of intent were exchanged between the UK and French defense ministers in advance of signing the official MOU prepared by Germany, Italy, Spain, Sweden, and the UK. The French officially joined the program in September 1999. In July 1999, the Swedish Air Force announced that it would not be funding development of Meteor due to a shortfall in the defense budget. However, this decision was not expected to affect Sweden's participation in the program, with funding being found from other sources. The political stakes were high. On August 4, 1999, US President Bill Clinton wrote to the UK Prime Minister, Tony Blair. Clinton said that "I believe transatlantic defense industry cooperation is essential to ensuring the continued interoperability of Allied armed forces." Blair also faced lobbying from the French President and Prime Minister, the German Chancellor, and the Spanish Prime Minister. In response, Clinton later wrote a second time to Blair, on February 7, 2000, timed to arrive before the February 21 EAC meeting to discuss the decision. He put the case for Raytheon's bid, underlining the phrase "I feel strongly about the decision." The direct intervention of the U.S. President emphasized the political and diplomatic significance that the VRAM procurement had acquired. In autumn 1999, Raytheon offered yet another twist to its staged approach with the IRAM Plus. If chosen, the U.S. government, in an unprecedented move, offered to merge the U.S. AMRAAM and UK VRAM programs, under joint control. IRAM and would be adopted by both countries, equipping Eurofighter, JSF, and the F-22, allowing economies of scale from large U.S. procurement. IRAM and would retain the IRAM dual-pulse motor but fitted to a front end incorporating all the features of Phase 3 of the U.S. Department of Defense's DoD, AMRAAM Pre-Planned Product Improvement, P3I, program, which was planned out to 2015. These included upgraded seeker hardware and software to provide improved performance against advanced threats and replacement of the longitudinally mounted electronics boards with a circular design which reduced the volume occupied by the electronics, allowing space for a longer rocket motor. As equal partners, the US and UK would jointly specify and develop the new missile. It was estimated that IRAM and could be delivered for less than half the budget allocated for VRAM with a 2007 ISD. According to Raytheon, the program would have initially provided the UK with 62% of development, production, and jobs for the mod VRAM procurement and would give the UK 50% of the significantly larger US air-to-air market. The UK would have participated in the production of every AMRAAM derivative sold around the world, projected at that time to be about 15,000 over the following 15 years. The ARC dual-pulse motor would not enable full compliance with the SR.A. 1239 requirement, however it was believed to be adequate to counter the threats expected until 2012-15 when improvements to the warhead, data link, and propulsion would be available. The slow pace of Russia's ramjet-powered R-77 derivative, a mock-up of which had been displayed at the Paris Air Show but which had not progressed past component ground tests and for which the Russian Air Force had no requirement due to lack of funding, was offered as evidence that the full capability required by SR.A. 1239 would not be necessary for some time. At a press conference to launch Iran, and Raytheon said that a ramjet power plant is not needed today. Countering Raytheon's proposed transatlantic tie-up, Boeing was added to the European team, to provide expertise on aircraft integration, risk management, lean manufacturing technology and marketing activities in selected markets. Boeing also brought vast experience of dealing with the U.S. DoD, essential in any future attempts to get Meteor on U.S. aircraft. Raytheon were delighted that MBD has validated our transatlantic approach. Although initially interested in developing a suppression of enemy air defense variant of Meteor as a successor to HARM, Boeing has become less and less an active partner as development has progressed, possibly having served their political purpose. In late 1999, in advance of December's EAC meeting to discuss the BVRAM competition, Sweden rejoined the program. By early 2000 both teams had submitted best and final offers. The government was expected to announce a decision in March, following a meeting of the EAC on February 21. The decision was so politically delicate that some believed that the EAC would leave it to the Prime Minister when he chaired the Defense and Overseas Policy Committee. MBD announced a proposal to work with Boeing to offer Meteor-derived technology to the US. MBD and Boeing urged the US to agree to a governmental-level transatlantic cooperation on the Meteor program. In a last-minute bid to sway the decision, Raytheon proposed increased European involvement in its program. Last-minute intervention by the UK Treasury delayed the decision, after concerns about the cost of Meteor, believed to be the preferred solution, compared to the cheaper incremental approach offered by Raytheon. Decision. In May 2000, the UK Secretary of State for Defence, Jeff Hoon, announced that Meteor had been selected to meet SR.A. 1239. Fabrice Bregier, then Chief Executive Officer of MBD, said this decision marks a historic milestone in the establishment of a European defence capability. For the first time, Europe will equip its fighter aircraft with a European air-to-air missile, creating interoperability and independence to export. By this stage the in-service date was 2008. The British House of Commons Defence Select Committee summarised the reasons behind the decision in its 10th report. The Meteor missile has some clear advantages over its Raytheon competitor. It appears to offer the more militarily effective solution. It should help rationalise and consolidate the European missile industry, and provide future competitions with a counterweight to US dominance in this field, and it entails a lower risk of constraints on Eurofighter exports. Although the program is in its early days, it also offers the prospect of avoiding some of the problems that have plagued other European procurement collaborations, without arbitrary work-share divisions and with a clear project leadership role to be provided by the UK. The MOD needs to take advantage of that leadership role to keep momentum behind the project, including an early contract which will lock in not just the contractor but also the commitments of our international partners. The cautious definition of the missile's target in-service date may be realistic, particularly in view of the technological challenges that will have to be overcome, but in BVRAM's case it is a date that must be met if Eurofighter is to fulfill its potential. The selection of Meteor was not a total loss for Raytheon, as the UK ordered a number of AIM-120s to arm Eurofighter on entry into service, which was expected before Meteor development was complete. Pre-contract. Negotiations to conclude a smart procurement contract continued. At the Paris Air Show 2001, defence ministers from France, Sweden, and the UK signed a Memorandum of Understanding committing their nations to the Meteor programme. The nations of the other industrial partners, Germany, Italy, and Spain, only signalled an intention to sign within a few weeks, claiming procedural delays within their national procurement systems. Following parliamentary approval in August, Italy signed the memorandum on September 26, 2001, for an anticipated procurement of about 400 missiles. Spain followed on December 11, 2001. Germany's financial contribution to the program was considered essential, but for more than 2 years development was hamstrung by the repeated failure of the German Defense Budget Committee to approve funding. Without the German propulsion system, MBDA deemed that Meteor could not realistically proceed. During this gap in the program, MBDA was funding Meteor from its own resources and, by June 2002, had spent around £70 million, most of which had gone, ironically, to Bayern Chemie to reduce technical risk in the propulsion system, the performance of which was critical to meeting the requirements. Germany had set 2 conditions for participation in the project: that the UK should place a contract for the weapon, and that MBDA give a guaranteed level of performance, both of which were achieved by April 30, 2002. It was hoped to sign an agreement at that summer's Farnborough Air Show. However, Meteor was not on the agenda of the German Defense Budget Committee meeting on the July 3, which meant that a decision could not be made until September 12, after the German parliament took its summer recess. This was claimed to have been due to a delay in paperwork being transferred between the defense and finance ministries. However, there were concerns that this meeting might not even happen until after the German elections on September 22, which would push a decision to the last quarter of the year. An article in the German press claimed that the Rechnungshof, independent federal audit division, urgently recommended to work up an alternative solution in US-European cooperation and to negotiate a solution with the foreseeable partners because of the recognizably high risks in all areas. These delays led to high-level diplomatic contacts over the summer, with both the UK and Italian defense ministers writing to their German counterparts stressing the importance of the Meteor program. Germany finally approved the funding that would allow development to commence in December 2002, but at the same time cut its planned acquisition, from 1,488 to 600 missiles. Description: Seeker. Terminal guidance is provided by an active radar homing seeker, which is a joint development, June 2003, between MBDA's Seeker Division and Thales Airborne Systems and builds on their cooperation on the AD-4A, active anti-air seeker, family of seekers that equip the Mica and Aster missiles. Thales produces 4 sub-assemblies representing approximately 35% of the seeker. Forebody. Immediately after the seeker, the missile Forebody, which is designed and manufactured by Indra Systemas, contains the inertial measurement system, IMS, provided by Litev, a German subsidiary of Northrop Grumman. The active radar proximity fuse subsystem, PFS, is provided by Saab Bofors Dynamics, SBD. The PFS detects the target and calculates the optimum time to detonate the warhead in order to achieve the maximum lethal effect. The PFS has 4 antennae, arranged symmetrically around the forebody. The impact sensor is fitted inside the PFS. Behind the PFS is a section containing thermal batteries, provided by ASB, the AC Power Supply Unit, and the Power and Signal Distribution Unit. Warhead. The blast fragmentation warhead is produced by TDW of Germany. The warhead is a structural component of the missile. A telemetry and breakup system, TBUS, replaces the warhead on trials missiles. Propulsion. The propulsion subsystem, PSS, is a throttleable ducted rocket, TDR, with an integrated nozzle-less booster, designed and manufactured by Bayern Chemie. TDR propulsion provides a long range, a high average speed, a wide operational envelope from sea level to high altitude, a flexible mission envelope via active variable thrust control, relatively simple design, and logistics similar to those of conventional solid fuel rocket motors. The PSS consists of 4 main components: a ramcombustor with integrated nozzle-less booster, the air intakes, the interstage, and the sustained gas generator. The PSS forms a structural component of the missile, the gas generator and ramcombustor having steel cases. The propulsion control unit electronics are mounted in the port intake fairing, ahead of the fin actuation subsystem. The solid propellant nozzle-less booster is integrated within the ramcombustor and accelerates the missile to a velocity where the TDR can take over. The reduced smoke propellant complies with Standard 6016. The air intakes and the port covers which seal the intake diffusers from the ram combustor remain closed during the boost phase. The intakes are manufactured from titanium. The interstage is mounted between the GG and the ram combustor and contains the motor safety ignition unit, MSIU, the booster igniter, and the gas generator control valve. The gas generator is ignited by the hot gases from the booster combustion which flow through the open control valve. The gas generator contains an oxygen-deficient composite solid propellant which produces a hot, fuel-rich gas which auto-ignites in the air which has been decelerated and compressed by the intakes. The high-energy boron-loaded propellant provides a roughly threefold increase in specific impulse compared to conventional solid rocket motors. When it enters service it will yield a no-escape zone more than 3 times greater than that of the current AIM-120 AMRAAM used by Eurofighter Typhoon-equipped air forces. Thrust is controlled by a valve which varies the throat area of the gas generator nozzle. Reducing the throat area increases the pressure in the gas generator which increases the propellant burn rate, increasing the fuel mass flow into the ram combustor. The mass flow can be varied continuously over a ratio greater than 10:1. The Meteor PSS will be able to cope with high incidence and limited side slip angles during maneuvers but not negative incidences or large amounts of side slip. Control. The missile trajectory is controlled aerodynamically using 4 rear-mounted fins. Meteor's control principles are intended to allow high turn rates while maintaining intake and propulsion performance. The fin actuation subsystem, FAS, was originally designed and manufactured by the Clave Ram Group, formerly Ferry Hydraulics Limited, a Somerset, UK, based division of the US company Hamilton Sundstrand. Currently the design has been taken on board by the MBDA UK, at Stevenage. The FAS is mounted at the rear of the intake fairings. The design of the FAS is complicated by the linkages required between the actuators, which are located in the intake fairings, and the body-mounted fins. Data link. Meteor will be network-enabled. A data link will allow the launch aircraft to provide mid-course target updates or retargeting if required, including data from OFFB or third parties. The data link electronics are mounted in the starboard intake fairing, ahead of the FAS. The antenna is mounted in the RE.
Please subscribe and thanks for watching.